in the first module named sync, the value is being updated on the first module or the first clock cycle, and this is being reflected at the second clock cycle of the another module. Okay, this is what we actually mean that there is a synchronization program between different modules. So if we wanted to eliminate this, we need to use a synchronization logic. So we can eliminate this, and we have done this by the help of synchronization flag.
And how did you synchronize between the different clock regions?
In terms of synchronization, as I said you earlier, we will be using a synchronization flag. And we have also used request and response method for handshaking between algorithm and XP transmitter. So why we have used this method is like we doesn't want to transmit a single message over and over again. So we have used something like a message start transmission, in which the XP transmitter will start the message to be transmitted. And after that, the XP transmitter completes its transmission, it will indicate backwards to the algorithm like the transmission is completed.
Internal structure of FPGA consists of basic, at the most root level, it's just a bunch of mux and a D flip-flop and some other logic elements inside it. So what happens is that when we try to use a for loop like we were using previously and 2D arrays, so it doesn't know how to actually synthesize a for loop, because for loop for a specific number of iterations also would need it to connect the multiple elements in daisy chain or some other way, which was making very difficult for it. So, and also 2D arrays doesn't actually have support for in Verilog. We were able to get the compile for say 8 nodes, which I listed there. That 20 line code, the for loop array, it was getting compiled for we had a set of 8 nodes. As soon as I entered my 37 nodes, then it started causing all problems. So we realized that this is not the correct way, and also that everything has to be completed in a single clock cycle itself will have to put a lot of stress on the editor and the other parts of the compiler software FPGA. So we decided to use the state machine so that everything could be done in a single in one clock cycle. Every state was covered in one clock cycle, so that gave enough time for the fitter and also made the fitter effort to reduce very low.
Why is it necessary to complete it in one clock cycle?
No, sir, it wasn't necessary. It's just that the for loop, because as we know, the for loop will only exit once it completes. So the FPGA had to somehow manage to compute everything in that one clock cycle itself previously. But now we are using multiple clock cycles to compute it. As it is, we are running on 50 megahertz, so it's quite fast compared to the motor actuation. Motors have their own inertia, so it will take a millisecond for them to react. And here everything would be done in microsecond, even after say 100 clock cycles of the 50 megahertz loop.
When the synthesizer unrolls that entire loop at compile time, and then that entire block is then converted to logic, and it can be a huge combinational logic block.
Means that the more iterations you have in the for loop, the more size of the block is basically.
Break the original problem into enough interacting sub-problems until each sub-problem becomes sufficiently simple and small, and then go backwards, and then it's a very routine matter of coding it.
You don't realize that sensors are very sensitive to time of day, because the quality of the light in the morning is different from the quality of light in the late morning and afternoon and evening. Right? You take that for granted, but your sensors have to be programmed to adjust to that. A kind of normalization of that every so often in 0.75 seconds. We've done a number of experiments like that, where we've used the normal way of writing code bottom up. Then we've built a high level design in a state chart based way, only as a tool to help us think. And we find that our experience is that we do stuff in less than half the time, because a lot of the debugging becomes much easier. And when you can map the constructs at the high level into your lower level blocks, you also minimize the communication between them.
I felt that I did not need an integrator, because the way I sort of constructed the line following code, I had a lot of if and else statements that basically they used to nudge the bot into the black line if it was, straying away for too long. So I think that can't be called a traditional integrator, but I think that served the same purpose. So it reduced the steady state error.
What was your update rate for the bot's orientation?
As soon as the ADC finished sampling, it would send it to the line following module directly. So I think the ADC was running at 2.4 megahertz.
If you have such high sampling rates, maybe then you don't need PID, and P controller will do.
Yeah. I mean, it's that delta coding versus sigma delta coding, that debate. So simpler hardware, but more power.
All of the modules, they are clocked by the same 50 megahertz clock. I was looking online about how the design is done usually, and I came across clock domain crossing issues. And I thought that if I can avoid it altogether, like I felt no need to introduce multiple clock domains in the design. So I clocked everything via 50 megahertz from the start itself. The interface was very simple, like sometimes as simple as just one flag. And as soon as for example, the Dijkstra solver, as soon as it is done processing, it just raises a flag that I'm ready now, and you can fetch the path, the latest path. And that's how the top level state machine knew that the data is ready. So the path also was available to the top level state machine as it instantiated the Dijkstra solver. 25 clock cycle thing. First, I'd like to highlight that the graph that I made, that was of 26 nodes and not the full 37 nodes, because I wanted to simplify it further. So I eliminated all the nodes that were in the warehouse, and I handled all of them separately, since it was a much simpler task to do. Only the real-time navigation on the actual fields, that was done by the Dijkstra solver, and it had only 26 nodes. If we were to do it in traditional programming languages, we would iterate through an array, and the Dijkstra solver would find out that which is the minimum available path in this array. So it had to iterate it n times. Like if there are 26 nodes, it had to iterate 26 times, and it gave you that this is the shortest path. So I eliminated that thing altogether by using combinational logic. So I made a bank of comparators that took in 26 different numbers, and almost instantly it outputted the minimum path among all those numbers and the index of that path. So that can be used by the state machine. So basically, it used combinational logic instead of sequential to shave off a major chunk of execution time. So every clock cycle, it could evaluate one node. So since there were 26 nodes, I managed to finish the whole computation in 25 clock cycles, since the first node is already pre-computed. Everyone has experience in C and Python. So relating to that experience, they try to fit it into Verilog. So they expect the same behavior from Verilog. So they end up choosing Verilog implementations that mimic the C-based implementations, like using iterations. So that would be the first thing, is that to unlearn the previous things that you've learned and actually understand how synthesis is done and how Verilog is translated into actual digital circuit.
The notion of a model. Most of them don't have a clear notion of what model they are using as the basis of their work. So for example, if you are talking about a synchronous single clock model, Jugal had, for example, internalized that model. Let's call it a synchronous paradigm. And the second part was the planning or top-down nature of the design process. Most people are not giving enough weightage to that or enough importance to that. And then of course, there are some basic things like how to write the Verilog, what is or Verilog or VHDL, and what the synthesis tool does.
When we write programs, we never think about concurrency and hardware description language. The moment someone says SDL, it's actually concurrency, because hardware actually runs concurrently. Yeah. But as programmers, we think sequentially. That's where the gap comes from. So maybe that will be a high-level GAN for your juniors if you want to provide.
When you're talking circuits, every transistor can be firing in parallel, and that's the power of hardware. Thank you all very much, and God bless. Jai Hind.